All right, so let's see, we were discussing of some rather gory details, I should say, of one example of an active mode locking scheme for getting very sharp pulses of very high intensity laser output. So that was the topic that we were talking about in the last class, and at least the concept I hope is clear, if not the mathematical details, but at least the concept was that if we start with a gain medium and in its path inside the laser cavity I introduced another modulator, an optical modulator that lets through light at with a transmission which is a function of time, and the way we were looking at in the last class was that essentially we came up with a mathematical formula for the time dependence which looked like a sine square with a certain frequency by 2. And physically what it means is the light that's going through as a function of time, the transmission coefficient as a function of time will go low and then go high and then get low again and high. So it looks something like that. Now, one can make a plot of that sine square function, right? And as a function of time, it's going to look something like that. And obviously this frequency would be related to omega m, 2 pi by omega m. And so you can basically start thinking about, I have initially, you might think a laser pulse, first of all, it's oscillating at a very fast frequency, but then the amplitude of it, as it goes through here, you can see that it will be cut off in a certain way. And what will come out is, instead of a pulse which is uniform in amplitude, what will come out from here and then maybe reflect back is something that starts looking something like that. It has a pulse shape like that. So it gets shaped by that. And after a few rounds, it essentially, you kind of lock into the shape of the pulse locks into the frequency of modulation here, and that's the locking we're talking about. And so we went through a bit of mathematical details of that. As an example, I think this probably is probably is one of the more complicated things you're going to look at in this class. But what we started out was we said that because we know that all this modulation will occur, and I'll have a pulse, and the pulse will look perhaps, something like this, with this frequency is related to, I'm plotting it versus time. So what is this frequency related to? The small oscillations for the laser pulse. That, the very fast oscillation. So what are we plotting? We're plotting, you can imagine we're plotting the electric field as a function of time, right? So what is that one related to? Or how do I know the period of this oscillation? Anybody help me with that? Yeah. Yep.
1 over the frequency.
Right. Frequency of what? So no, that's right. Frequency of the light itself. It has nothing to do with the modulator at all. So exactly. That's right. So if you have, if you know the wavelength of your light pulse, red or green or blue, this is essentially just 2 pi, or it's the wavelength is this is the time period, right? So it's 2 pi. Or 1 over your nu naught, or whatever you can call it, right? 2 pi by omega naught, or 1 over 2 naught, right? So, right? And that is just related to the wavelength of the light. Whereas what we are talking about is the shaping of the amplitudes here, or the pulse here, right? And this is going as e to the power minus t over a certain pulse width. So this would be our pulse width. And I'm going to discuss this with a couple of examples today, whole squared. So that's what you kind of have here. And if you want to kind of normalize it, when you integrate it over all time, you want it to be 1. And that's why there's this kind of a 2 minus 2 natural log 2 factor sitting out, so it's just a normalization factor, okay, and etc. So I mean, I hope it's clear what we're doing. So therefore, the total electric field amplitude, this is electric field, this is the Euler E 2.71 and all that. The total electric field will be, this is the modulation, and then you have the fast rate, which is e to the power j omega naught t. Omega naught is this frequency now. So it's just, that's related to the wavelength of light, whether it's red laser or green or blue, whatever, right? Infrared. So the total electric field will have your Gaussian shape and that. And now we are propagating it through a gain medium, and the gain medium has its own gain profile as a function of frequency, and the gain medium might be looking like well, nu or omega. I hope you can, so you can convert between nu and omega. And we have talked about various ways of thinking about gain. You can have homogeneously broadened gain spectrum or inhomogeneously broadened gain spectrum, but we know that, right? Nu. And so that's a function of frequency of the light that's going through, and that's what we're writing. We kind of cook up a certain gain spectrum, and then we move this light through. We are moving it through, we start out in time domain. This is the time domain behavior. But the same thing if you go to frequency domain. I think you know that in the frequency domain here, we can write it in maybe omega frequency. So how will it look in the frequency domain, this Gaussian pulse? So first things first. Physically, at what frequency are most of the oscillations here, right? So they are centered around omega naught, right? So that's clear. Very, most of the oscillations are occurring with a frequency of omega naught in time domain. So you will kind of get, first of all, a strong peak at omega naught, a lot of signal at omega naught, and then you will get, because it's a Gaussian, you will also get a Gaussian shape. That's one function that doesn't change when you go into Fourier domain. In time domain, this part is Gaussian, and so it is in Fourier domain. So essentially, you'll get something which will probably look something of this nature, and this envelope here would be your omega minus omega naught squared. So that's the Gaussian sort of function, and now, I think you see that I'm plotting in this way, but you do have all frequency components here. It's not like you have just a discrete set of frequencies. You do have, whenever I have a pulse like that, I do kind of spread this out. And this is your spread in the frequency domain, delta omega, which is related to the spread in the time domain. And I think the product of this is the smallest for a Gaussian, time domain and frequency domain. Smallest for a Gaussian. Any other shape you choose will have a slightly bigger product. Okay. So anyway, we propagate this through here. In the gain medium, we find the gain the electric field in frequency space, the gain in frequency space, multiply it, and recover this. I have a little reflection here on the side. Recover this. By the time I reach here, I have 2 gain passes, so square. And then I go back to time domain, find my time domain electric field, and it still remains a Gaussian, doesn't change the shape, still remains a Gaussian in time, and still remains at the same frequency. But other things have, the coefficient has changed. Obviously, I have much larger amplitude. I've gone through a gain medium, so I might have started out like that, but I come out like that, right? By the time I have gone through the gain medium twice. But the frequency hasn't changed, and but it has actually, there will be a little bit of a modification in the pulse width, and that's where this Q appears. Here the width was related to this delta TP over 2 log 2, which is A. Here the Q, it depends on A, but there's a little extra change because of the gain medium. It reshapes it a little bit in the frequency domain, and then you pass it to the modulator, which does that, right? And then by the time you come out of the modulator, there's again a little bit more change in A, which is the shape of the pulse. It's reshaped, and it has some imprint of the modulator frequency in the pulse width now. So and the frequency, by the way, hasn't changed either. It's still omega naught. And then you equate this to the original function, and then it tells you what are the conditions for gain. That's for you to be able to laze and still have the mode locking and get the pulses out at a repetition rate. So that's kind of the mechanism we went through. And today what I want to talk about is what kind of modulators do you use? And for example, in a laser, typically in a mode lock laser, this modulator could be either active. This is clearly an active modulator where you are doing something. You are not just sitting at one transmission coefficient, but you are actively modulating it, right? That's what you call an active modulator. You can do it either in amplitude domain. So this is an amplitude domain modulator. And the other thing I had mentioned, I don't want to get into details there, is if you, instead of a sine function, if your transmission function is e to the power j, so now it's complex, that's real, times, again, some amplitude times a cosine of omega mt. If you choose this sort of a mathematical formula, this is actually a frequency modulation, not an amplitude modulation, but frequency. And then what it'll do is it will introduce, if this is the pulse going in, or let me sketch it here. Let's say, this is the pulse going in. So, you have the same frequency throughout in time domain here. But if you introduce this, take it through the modulator with a transmission coefficient like that. So first of all, you can see it's going to change the phase with time. This is a time varying phase. Anything that sits to the right of j in a transmission coefficient, that's a phase, right? And it's changing with time. It's a time dependent phase, and it's going to add a time dependent phase to the signal. And what's going to come out here is again a Gaussian, except inside here it may be oscillating slowly here, and then as you go out here the frequency may get much faster, and then it will kind of die down again. So essentially, if you plot the frequency omega as a function of time, for the AM modulation the omega is omega naught always in time. But here the frequency is going to change. For example, it can change from omega naught before the pulse. So it may change from omega naught, and it can maybe linearly increase. I'm exaggerating it. The increase will be very small because omega naught generally is extremely high. We're talking hundreds of terahertz. That's the frequency of light wave. And the modulator would typically be in a gigahertz or something like that. So you will increase a little bit, but essentially the frequency can increase, and this is what would be called. So one can write it as omega naught plus, some delta omega times t over big T, or delta pulse. I'm just cooking this up, but essentially you can linearly increase and have a little change over the end of the pulse. And so that would be what's called the chirp or frequency change inside a pulse, right? Just like the chirp of a bird. So that's a FM active modulation for a mode locking laser. So the frequency can essentially change in every pulse, in the beginning to the end of the light wave can just shift a little bit. Does it make sense? The frequency shifts, therefore the wavelength shifts just a teeny bit. Just remember that this is 100 terahertz and we're talking about a gigahertz here, so it's not a big change, but it's still a change. You can kind of detect it. The frequency is easily measurable. So those are the two active modes of locking a laser and getting pulses out. And I think you can see here that just because of this nature, actually I want to try using this here. Let me see. Okay. So yeah, because of the nature of the pulses, let's see. Oh, it does work. Nice. All right. Because of the nature of the pulses, this is when e to the power, you get a 0, that's 1 transmission. And this is when you have the minima, right? And that's the ratio of how much you cut off from the pulse, and such things. And what I want to do next is, you can imagine that the moment I introduce anything that has a transmission coefficient is always equal to or less than 1, I'm losing power. It gets absorbed. Some of it is lost. And then this modulator is an active modulator. But many times, in fact, for most semiconductor technology, you don't use an active modulator. You use a passive modulator. And a good example of that is what's called a saturable absorber. And I think Cliff had mentioned briefly. We're going to look at it in a little bit more detail. In fact, we're going to generalize the concept of a saturable absorber and say that we can also have something called a saturable amplifier. Absorber is just something which has a negative amplification coefficient. So we're going to generalize the concept and look at this idea of what is a saturable amplifier or saturable absorber. And so first things first, it is a passive a locking element, if you might, as opposed to, say, the Pockels cell or some other amplitude or phase modulators which are active. So this is a passive locking element. First of all, you realize that not only are we losing energy in that, we are also putting in energy to modulate it, because this modulation is not coming for free either, right? So that's another thing which needs a battery, which needs power too, right? So you're cutting down the efficiency of the whole system. On the other hand, if I had a saturable absorber, it's going to just sit there. If you're not operating the laser, it's not going to consume any energy, right? I mean, and such things. And a passive locking element, I'm saying this is for locking, but in general, it might first seem weird. How can a passive element actually mode lock? But I think we'll see now it does. And the other kind of nice thing about using, so just as a comparison, we have talked about Q switching, right? And now we are talking about mode locking, and both are going to give us pulses in time, of laser pulses in time. The Q switching, remember the mechanism was you pull the gain medium way out of, in a very heavy population inversion, way larger than the threshold. And that you do by not having, you kind of spoil the Q of the cavity, therefore there's no lasing. So the material can be as population inverted as you want to be. Typically it's maybe 4 times or 5 times that of the threshold required for lasing. And then suddenly you open a shutter, or you create a situation that you reach resonance, and then it dumps out a lot of power in one go. So it dumps out a lot of power, and not just that, it actually dumps out a lot more energy than you can get in a CW way. A lot more energy, because you pull the gain system way out of the threshold, way above the threshold. So that's Q switching. You get a lot of energy in per pulse. Energy. So energy would be integrated power. But mode locking, what we are doing here is we are taking the CW sort of energy, CW output power with time, and we are generating, compressing it into very sharp pulses, right? But the total energy, we can get a very high power here, but the total energy is actually quite a bit smaller than the Q switching. Q switching gives you a lot more energy per pulse. In joules, we're not talking watts now, joules. The area under the curve is way larger, because here we are really not pulling the system out of way out of the threshold. We're not really pulling it out. The gain medium is still kind of locked around threshold. It's just that it's pumping out pulses with some time intervals, because it's mode locked, but its gain medium is not like 5 or 10 times out of the threshold required for lasing, for the mode lock. Does that make sense? The mode lock total energy per pulse is actually quite low compared to a Q switch. Both of them are way higher than the CW. So if you let the CW go continuous wave, then with both techniques you can get much larger pulses, but the total energy here is low. And to kind of remedy that, and you can see we're kind of going in circles, but it actually, to remedy that, you can make a mode lock laser also go through, to kind of increase the gain. You can have an additional gain element, and that's what one would call a saturable amplifier. And this is not for locking. And then for locking, on the other hand, you can have a saturable absorber. And what I want to really talk about today is that both are really, the physics is the same. We just want to understand how they work. That's really what we want to do now. So both are passive elements. Actually, let me put it this way. Saturable absorber is clearly a passive element, and I think you can see right away that, and you cannot get an amplifier which is passive. That's not possible. You want to have, so the saturable absorber is indeed a passive locking element. Saturable amplifier, even if you don't want to lock your laser, it's fine. You can use a saturable amplifier regardless. Whether you want to make a laser or you just want to amplify some light, you can always use it. So we're going to look at this concept first, and the idea again is we are going to introduce an element inside the laser, maybe a thin layer of something, and what we are saying is we have first, we have a pulse that's incident on it, right? And the pulse is looking something like that. It has a little shape, which is Gaussian here, and it's oscillating at its own center frequency and all that, right? And so it has some amplitude variation because it's a time domain pulse. And then when it comes out, after it gets either amplified or absorbed through the saturable absorber amplifier, its pulse is going to be reshaped. It's going to look slightly different. The pulse shape is going to look different. And when it's going to come out here, maybe the pulse has grown in size, maybe. If you have a saturable amplifier, and maybe the frequency has not changed at all, or it has shrunk in the case of a saturable absorber. Okay. But why is it called saturable? Is because if I look at saturable absorber, it's as a function of intensity, the absorption coefficient is, initially you have very high absorption coefficient, but at some point you reach a certain let's call it a saturable intensity, and then it kind of drops very sharply. So you can see it's kind of a window through which the light is going to go initially for less intensity. If the intensity of light, which is the amplitude of this, is small, it really gets absorbed. Right? But if the intensity grows very big, if the intensity becomes very large, the window becomes transparent. So it saturates all the possible absorbers in there. Every atom that can absorb that photon has done the job by the time. So when I start out the pulse, the leading end of the pulse, it starts getting absorbed because intensity is not very high. Right? Intensity is kind of an integral of how many photons you have over this. Does that make sense? It's kind of summing over all the maybe let me step back a little bit. Remember, this oscillation is extremely fast, right? This oscillation is occurring at 10 to the power 14 hertz or 100 terahertz, right? Light absorption is much slower than this. When an atom or any absorption, you have quantum well, quantum dots, dyes, whatever you choose here, this frequency is way too high. So it's going to kind of look at this kind of like a DC. It's just going to integrate over that. So, and as it does that, it starts getting absorbed. So every atom that could potentially absorb, so the intensity with time is increasing. Does that make sense? As the pulse goes through, inside here we're sitting, the intensity is increasing, and at some point you're going to reach, and so the intensity is getting integrated. And at some point you're going to reach threshold, and then it's become completely transparent. It cannot absorb anymore. Does that make sense? So it's saturated. So it cannot absorb anymore. Its absorption coefficient suddenly drops, and then this window is open, and it goes through. Right? So it's as if physically what's going on is the pulse shape itself. The pulse shape itself. The leading edge is low intensity, and as you go back, as the pulse goes through here, right, it's integrating. The area here is the intensity, and at some point you reach the threshold, right? And then beyond that, the pulse doesn't get absorbed anymore, and it goes through. The whole energy goes through. Right? So that's the idea. It's as if you have, the light itself is turning the switch. Does that make sense? The intensity of light itself is turning this. It's automatically toggled by the light itself, the pulse of the light itself. Yeah. So that's physically the meaning of a saturable absorber. And in a certain way, I drew the amplifier, but if you kind of, if you reduce the amplitude, that's the absorber. Does that make sense physically at least? You know, and the rest of it is now we can go through the math and understand how this works. So a saturable absorber would be just a plate. If you look at a semiconductor device, in fact, you have, and I'll describe it a little later, in a semiconductor laser, which is mode locked, what you do is you have an active region. So you pump the active region, and that's how you create a gain medium. And you just leave one part of your sample. You can just sketch it here. So in a semiconductor laser, what you do is you will, and we'll discuss this in some more detail later. You have quantum wells and all that. And then this is and you inject current. You excite it by injecting current. And this region is what is your gain medium. Right? So wherever the current is going through, that's how you're exciting it. So that's you have gain there. Right? But what you do is after you grow the material in the lab, you can now kind of come in and etch through a little window here. Okay? Etch through a little window. And then you decide that I only want to inject current here within this window, and I don't want to inject current here. Leave it as it is. So this region is the same material as here, but this region has no current. Therefore, this region is sitting as a passive absorber, because now since you're not injecting any current, you don't have any population inversion here. It's not population inverted. Whereas here we're injecting current, therefore in this region I have population inversion. So this is, you know, getting stimulated emission and all that. So the light is coming out here, and right next to it is this is a saturable absorber. It's sitting right there with no excitation, therefore it has no gain. In fact, it has a little bit of loss, but it's a saturable absorber. It can only absorb a certain density of photons, right? So the light goes through and goes through here, and this is a cleaved facet, for example. It reflects, and maybe you can put one more. Generally, people just put one. It goes back and forth, and the light that will come out from the end here is already mode locked. You don't have to do anything else. It's just, you know, very simple in that sense. So I'll talk about this in a little bit more detail later when we talk about semiconductor mode locked lasers. Many other things, you can use dyes and all kinds of other, a lot of quantum dots typically used, because then you can control the intensity at which you bleach or, you know, saturate it, because you can change the density of dots, and you can control how much saturation intensity do you need. So that's just a qualitative overview of what is a saturable absorber. And we want, if you turn the story around a little bit, you can now, you know, supply some power to this region, either optically or something like that, and you can also have a saturable amplifier. I mean, that's the opposite of it. Instead of a loss, you actually have gain now. But now you have to supply energy. You have to create, this region must also have population inversion. Only then you can have gain. Right? That much is clear, hopefully, right? Yeah. So let's go through how does this actually work, sorry, where is that? Okay, so there's a little bit of math here, but it's something that you have seen before with Cliff. The only difference now is these phenomena that we're talking about, the speed at which the pulse propagates, the speed, you know, of oscillations here, typically the length of the pulse. These things are so short, especially the frequency of light is obviously so fast that the saturable absorber is doing all its dynamics in a very slow fashion than the pulse itself. The pulse width, round trip pulse time, and all that. The pulse width, the saturable absorber's response is way slower. That's why it's kind of integrating over the intensity. It doesn't look all the details of oscillations, whereas you had earlier done very similar math with Cliff, which was for dynamics of Q switching. You will see the analogy of how we deal with this problem. It's exactly the same, really, except here the saturable absorber's response time is way slower than all the other time constants in this problem, like the oscillation frequency and the round trip, the distance in time between the pulses. This responds slower. That's why it kind of integrates over all these things, and then you get, it depends on intensity and not the details of the time. So let me now just go through, once we understand this, what we now need to find out is, if I know my intensity as a function of time in my input, that's what I'm going to call I1. Intensity as a function of time in my input here. what is the intensity as a function of time in the output? That's really the, once you can write that down, you have completely characterized your saturable amplifier or absorber, whatever that is. Does that make sense? So that's the problem we want to solve. What is I2 as a function of I1? And here's, let's say, the length of this region is L. We'll just label it as L sub G, though in an absorber you may not have gain loss, but just L sub G is the length of this region. Okay? And the pulse is going to go through, and what comes out here is what we are after, right? So I think we know how does intensity change in space, but now we want to also solve it as a function of time. That's kind of new here. No, I mean, you have done this in Q switching, but I just want to say that if you want to answer the question, how does that change in time? How does it change in space, let's say, right? You can use, to be more accurate mathematically, partial derivatives. How does this intensity of any pulse change in space? I think you know this, that the intensity will grow in space if you have gain. It will decay in space if you have loss, right? Rate of change of intensity in space is proportional to itself times the gain coefficient or the loss coefficient, right? That's something we know already. And what is the gain coefficient or loss coefficient? It's cross section times your N2 minus N1, right? And what is that? I over H nu, sigma I over H nu. All right, so that's your gain coefficient. I think I was writing some extra terms. Okay, cross section times population inversion. That's what we call as our gain coefficient. Typically, it's written as a function of nu. We are kind of suppressing all those, things right now. Is that clear? The rate of growth of intensity is just proportional to the gain coefficient. So if I have nothing else, there's no other, spontaneous emission, then the intensity will grow exponentially because the solution to this equation is an exponential, right? E to the power gamma z, right? So you get a gain of mg. But then you always have a little bit of spontaneous emission. So this is your gain, and spontaneous emission typically or absorption or losses. Let's actually forget about spontaneous. This is just a loss. I can have defects, whether I create or not a population inversion. I can have always some defects in the material, heat, other kinds of loss. So we just allow for that fact that there can be loss as well. So that's your full rate equation that one needs to solve in space. That's going to tell you in space how does it vary. And now I think as far as the dynamics of the problem goes, we want to know what is N2 minus N1. N2 minus N1 inside this saturable amplifier or absorber. N2, we're going to find it now as a function of time, assuming that it's thin enough that the spatial variation is very, very, very small. Let's assume that N2 minus N1 here, if I have, whatever atoms I have, whatever gain medium I've created, N2, N1, from this end of the saturable absorber to that end or saturable amplifier, it doesn't change. It's very thin, but it changes in time. Obviously, things are going to change in time in this problem because there's a pulse going through it, short pulse. Right? So we're going to now try to find what is N2 minus N1 as a function of time. And I think a good place to start is say that I actually do know that how N2 is going to change with time. That part I do know. That's going back to your effective Einstein equation or the rate equations, modified Einstein equation. So there you get what? Sigma I over H nu, right, times N2 minus N1, right? Plus some spontaneous part. And I'm going to actually throw out the spontaneous. I'm not going to treat with that. Okay. Is that clear? This is something, is the rate equation. The rate of change of N2, meaning if you have created more atoms in the top state than in the bottom state, and the rate at which the N2 will decay, sorry, there should be a minus. The rate at which N2 will decay is proportional to how much population inversion I have. Right? The more is the population inversion, the faster it decays, and then that's proportional to that. And there's the intensity sitting here, and I'm going to throw out my spontaneous part. I'm not interested in the spontaneous. I'm looking at typically the stimulated or the gain part at this point at least. You can retain it there. And now N2 Exactly. I mean, this we have done a few times, right? The rate of change of N2 is rate of change of N2 is I think this is a slightly modified equation, so we're going to write that. Now, what is N1 plus N2? That's the total number of quantum absorbers or emitters inside this material. Total number. That's not changing. Whether you have a pulse going or not, that thing is fixed. It's N. Fixed, right? Obviously, N1 as a function of time is changing, N2 as a function of time is changing, but not the sum. The sum is fixed. Right? And so what we can do is write N1 now as a I'm going through this in a little bit detail so that we so I'm throwing out the spontaneous, and I get total N plus N2. Right? And so I can kind of rearrange this whole thing, right? dN2 over dt. And you see I get 2 times N2, bring it to the left side, write it as 2 sigma I over h nu. N2 is equal to sigma I over h nu times big N, which is the total number of atoms or quantum emitters. And you can kind of massage it a little bit, make it a nice looking equation. If coefficients are the same, so you get a rate equation in N2. That's the total number of excited states inside the gain medium, or inside the saturable absorber. I'm just going to call it a saturable absorber. We are doing the theory for both amplifier and absorber. So we're going to now define a couple of things. We're going to just redefine this quantity here as W sub S. This is kind of a saturated energy, if you might. I mean, energy per unit area. H nu is the energy of the photon. Sigma is a cross-section area on W sub S. That's just a definition, WS. And all right, so let me make sure so W sub S is just the energy per unit area, H nu over 2 sigma. And then this I, the intensity, we're going to write it in a slightly different way. So intensity, right, if I take the intensity and I integrate it over time, remember intensity is in watts per meter square or centimeter square. I'm going to integrate it over time from the beginning, way before the pulse has arrived. I'm sitting here, t is equal to minus infinity effectively means before the pulse has arrived, and t is when the pulse is kind of inside here at some point t, right? I want to see how is the saturable absorber affecting the pulse as it goes through. So I start integrating from way behind, before the pulse arrived, till a certain time t. So I think you can see now physically, if this is watts per meter square, you integrate, this is what we're going to define as W of z comma t. And physically what it means is we are just converting from the intensity to an energy in joules. Joules per meter square. Joules per meter square. Physically it means how many joules have entered my saturable amplifier or saturable absorber. How many joules are inside it now at time t. That's physically what it means. So we're going to make, these are just definitions. I am not really fundamentally, we're not deriving any new fundamental quantities here at this point. But that's the integral of the intensity, and then that's the definition of this W function. And then you can see now the intensity, and there's a WS here, and then intensity. If I integrate the whole thing, I get a W over WS, and then that quantity, let me just make sure. So I think I missed that. W is the integral. And intensity, therefore, is the derivative of W, obviously the opposite of this, right? W dot z comma t, dot being time derivative, right? So that being said, what I want to get to now is write down a modified equation for the time derivative of the N2s, right? And what you get here is that dN2 over dt is, or plus, so W is a variable with time, but W sub S is a constant, and the ratio, basically if you scale W of z comma t over this Ws, which is just h nu over twice cross section. It's a constant, here. So your equation then becomes, it actually looks much simpler. You becomes u dot times n2 is equal to n over 2 times u dot. Okay. So remember, so this is our u, and u dot would be derivative of that, and that would just be intensity. Does that make sense? I mean, all we have done is redefined a few things here, that's all. And intensity over Ws is just sitting here, I over Ws. Just read it, right? I think that's, unfortunately, it takes the most time in describing what it is. So that's your new equation, and if we solve this equation, we can get n2 as a function of time. And I want to find that because I want to find the time dynamics of gain, time dynamics of the pulse that's coming out. How is it shaped? How does it look like? So I need to solve that equation now. And so this equation is actually the trick you use is on both sides. If you multiply by this quantity, e to the power, an integral of u dot dt, dt from minus infinity to t, which is essentially just e to the power u. I mean, that's all you do. So you multiply on both sides. You will notice that, remember, n2 is changing with time, but n is not. N is the total number of atoms. It's not changing with time. N2 is changing with time. When you multiply it by this quantity, you realize this becomes an exact differential, and you can solve it in one step after that. Yep.
How can we assume that Ws is not dependent on the power?
Right. So Ws is h nu over 2 sigma, right? H nu is the photon energy, which is fixed for you in the laser gain medium, and in wherever you created it. So the laser center frequency is fixed, and sigma is the cross section of the saturable absorber material. Whatever atoms you have, that's not going to change depending upon your intensity. Under extreme conditions, it may, but this is, because these quantities are not dependent on time for you. So that's why it's not changing at all. It's just in that we are solving a time, and within that time, and also we have the same saturable absorber material within this thickness, so those things are not changing in Z or in T. So that's right. So if I take this function here, e to the power u, and I multiply on both sides, you realize that this actually is an exact differential because d over dt of n2 times e to the power u. When you take a derivative, this thing will prop out a u dot here, and you have that here, right? So you get a derivative of this plus u dot that, you get all that. So essentially what I'm saying is you get a solution that looks like n2 is n over 2 e to the power u plus some constant, which we don't know. That's the solution to this differential equation. In time, where is the time? Well, it's sitting in the n2 depends on time, so does u. U is the total integrated energy that has entered the absorber. And so we can take this out here, and you get, here's how it looks. N2 is equal to the total number of atoms or in the saturable absorber on the upper state as a function of time is changing like that. So that's the solution to this equation now. So obviously we haven't finalized the solution because you know a boundary condition when your t is equal to minus infinity way before things started. Let's say I know under what conditions I've created this saturable absorber amplifier. I know what is my N2 at t is equal to 0. I know my N2, N1 at t is equal to 0. I know that. When I say 0, actually, let me say minus infinity. Long in the past, before the pulse has arrived, I know those two values. How many atoms are sitting here? How many are sitting here? I know that. So that's what I'm going to call as N2 0 and N2 and N1 0. So those are the quantities. How many of them are in upper state and lower state way before the pulse arrived. So as you can see, if N2 is larger than N1, I have created a gain medium. If N2 is lower than N1, it's a loss medium. Right? So that's the situation I'm in. But whatever be it, I'm saying I know my initial conditions at t is equal to minus infinity. And I also know that at t is equal to minus infinity, what is U? Physically, it is the energy that has entered into the absorber. How much energy has entered? into the absorber at minus infinity? Nothing. Pulse hasn't arrived, right? So that thing is 0 at minus infinity, right? U is 0, therefore e to the power minus u is just 1, right? And therefore what you get is n2 at t is equal to minus infinity is still the total number of this plus just a k because e to the power 0 is 0. So right away you find out what's the constant, which we didn't know, right? And that just happens to be, well, yeah, from here. And I think you know from here that n10 therefore will be n over 2 minus k because they should sum up to n, right? And then so right away you know what is n20 minus n10, and actually that's what we are after. And you also know what is k. So after all this said and done, what we get here is n2 as a function of time minus n1 as a function of time, or the population inversion. How is it changing as a function of time depends on delta n0 e to the power minus u z comma t. It's kind of a nice result. It's very useful. So at time is equal to minus infinity, way out in the past, before the pulse arrived, this thing is 0, and I'm just sitting there, nothing is happening. The moment the pulse hits, it brings in some energy, right? And right away, you can see it decreases your n2 minus n1. You know? If you have created a population inversion, it stimulates and sucks away more photons away from it. How fast does it? I mean, that's all governed by this function u of z over t. Does that make sense? If, on the other hand, you have created okay, I'm going to just kind of discuss that now. So that's delta n0. That's the initial population inversion for an amplifier. Delta n0 can be negative if you instead of an amplifier you are in an absorber situation. So that's a little bit detail there. And then so that's your equation really. So remember I said in order to solve that equation, which I seem to have lost now. Where is that equation? Yeah, the intensity equation. Right, n2 minus n1 times as a function of time, and then we had a sigma, right? So that was my times I. Sorry, yeah. So that's the equation I wanted to solve, and I said I don't know this, but now I do. I just found out what that is. So you just go in and plop that whole thing there, right? And you get your equation, and this equation is actually a reasonably useful equation, which is why it has this. It has a name. I think it's called the Franz-Cordova equation or something like that. You can look at your book. But the equation essentially now, after you plop it in, you take this n2 minus n1 population inversion as a function of time. And you plop it into your intensity equation, which we started out with. You just plop it in there, and then you end up with this is your kind of modified equation now, and you get an equation in. The energy is equal to gain times u dot. It's a little involved equation. I'm going to just write it in terms of u's times alpha naught u naught. You know? So it's a little bit of a involved partial differential equation, things changing with time, things changing in space. And there's a little bit of the loss term here. With the loss term, you can only solve it numerically, but without the loss term, I'm going to just throw that out. Okay, so this is the, remember we are after intensity, and u dot is related to the intensity. Rate of change of energy is intensity. So I'm going to just throw that out, say there's no loss. I'm going to assume I have a perfect, no unintentional loss other than the quantum emitters that I have. And I'm going to try to solve that, and that is actually easy to solve. You can just integrate over time first, and the time dots go away. And then you take your z here, bring your e to the power minus here, gamma, u e to the power minus u is equal to dz times gamma. So you kind of integrate both sides, you can get the solution very easily. What does the solution look like? It looks like this. E to the power u2 is the total energy on the output side. Here, u2 of t is the energy on the output side. What do I mean by energy? It's W of t over saturation energy. What is W of t? It's an integral of the intensity, minus infinity to t, over a certain saturation intensity. So we can. This makes us how much energy has accumulated till time t output. What's the output of the pulse coming out? That thing is related to input in a very interesting way. It's a complex, it's a somewhat of a transcendental expression. G naught is your gain. So remember, here you will get a gamma times Lg on the right side, and then you'll see that it's an exponent term. E to the power gamma times Lg is always your gain, right? Gain. So that's your gain term there. And here's how the equation looks: e to the power u2, 1 plus this. And the intensity is just derivative of that. I think you can see from here. Intensity, you take a derivative, you get of u2, you get the intensity. So the intensity of the output, or the energy of the output, you can relate it to the input now through these two equations. So any shape of pulse you can create, you say, well, here's my input, you'll tell you here's the output. Here's my input in intensity, here's the output in intensity. And you can make a plot of it. And that's the plot that is being shown here. I'll just maybe spend 1 minute finishing up what this means, and we'll be done with this thing then, and we'll be done with this chapter as well. Right? So what he's saying is, let's say I have a pulse with time that's looking like that. That's my input pulse, the amplitude of 1. Okay? So that's the input pulse. Right? Let's say I have a saturable gain medium or a saturable amplifier. I have created N2 minus N1 is larger than 0. I have gain. In that case, if the pulse changes in time like that, that's the input. The output has gain. So, for example, at 0.5, the gain, let's say we choose a certain number here. Maybe let's choose the 2. Okay. So the output has a larger amplitude than the input. Okay. But if I have loss, it has lower amplitude. So this ratio of this quantity to the input, that's your G naught. It's the gain. But that only happens in the beginning of the pulse. And then by the time you reach the middle of the pulse, the whole medium is saturated. It cannot do anything more. It cannot give you gain, and it cannot give you loss either. It's completely saturated, and it has become completely transparent. It handled everything that it could. It cannot handle anymore. It's saturated, and after that, basically all the pulses, whether you have gain or loss, they become equal to the input in the limit. So the tail end of the pulse goes through unaffected. The head part of the pulse gets amplified or decays. So that's how it is, and that's the end of it. Basically, you can go through the physics a little bit more and read up, but that's the detail. That's the physics of it. And please read up that. And in the next class, we'll just do a review of the chapters like 6 through 9 that we have covered, and kind of summarize it all over again, the time dynamics and the laser concepts, etc. So we did that on Friday. And I do have these office hours from 5 to 7. If you have any concepts, questions, assignment questions, or outside, please come by today as well as tomorrow. So please come by.